So let's start from where we left, and where we left was that there were two equations. One was in the valid in the linear region, okay, and the other was valid in the saturation region. But what happens between these two regions? Okay, what happens between these two regions here? We have no equation at the moment. So for this, we need to develop the square law theory. Okay, so let's see. So we start with the this two-dimensional structure of MOSFET, and we already know this equation. This is the equation of current. It is charge times velocity times the width of the channel, and we know that the velocity is mobility. So this is mobility times the electric field, and we also know that it is electric field is the slope of potential. Okay, and that they both have opposite signs. So if one is negative, the other is positive. So this we know from the energy band diagram. So we can put the value of Vx, okay, here, and we get this formula, and we can take the dx on this side. So we have current as a function of charge and voltage, and we can integrate this formula, so we get this equation. So this is the equation. If we want to find what? We want to find formula for charge as a function of voltage. So we want to find this formula. So we start with this simple case where we have a 1D MOS capacitor. So this is our gate, this is our silicon dioxide, and this is our semiconductor. So we know very well that when Vg minus Vt is less than 0, so the voltage at the gate is less than the threshold voltage. In that case, there is no channel and the transistor is off, so there is no charge in the channel. But when the difference between potentials at the gate and threshold is greater than 0, then we know that we have this formula, okay, that charge in the channel is Cox, which is the oxide capacitor, times Vg minus Vs. We know this formula from the previous slide, and we said that the value at the our reference point, virtual source, remember virtual source, it was equal to this. So if we want to consider the full transistor, then let's see what will happen to this charge. So for along the x direction, if we go from 0 to the length of channel, we already know when we were discussing the pinch off point that there is a voltage Vx, okay, and this voltage varies along the channel. So at V0, which V0 is our virtual source, this voltage is 0. Okay, remember that this voltage is due to the drain. Okay, and at the other end of the channel, at V, when x is L, okay, so this is when x is 0, and let's say this is the point when x is L. Okay, so at the virtual source it is 0, V sub 0 is 0, and V sub L is equal to Vd. Okay, so we already know that the charge is at the virtual source is minus Cox times Vg minus Vt, and we are what is called, we are considering an approximation that is called gradual channel approximation. So what is the gradual channel approximation? The gradual channel approximation is that electrical field in horizontal direction is very less than electric field in the vertical direction. So the vertical field is very strong. In that case, the threshold voltage, because the threshold voltage is related to the gate voltage, which is in the vertical direction, it is the threshold voltage plus Vx. Okay, again Vx is our drain induced potential in the semiconductor. Okay, so it adds up with that. What this means is that now you are under the gradual channel approximation, your gate voltage should overcome not only the threshold voltage but also V of x. So we can put this V of x in our equation. Remember, this is the same equation that that we use when we were discussing the pinch off. Okay, so we include this term, and now we put that formula here. Okay, so instead of Q, we put this and we integrate, and if we integrate, we will get this formula. Okay, now this is a formula that smoothly connects the linear and saturation region in a square law device. What do you mean by a square law device? A square law device is the one in which the current saturates like this. So this is our IDE and this is VDS. So this is square law device. Okay. So this is also called the equation is also applicable to what is called triode region. What is triode? So triode region is basically, you can say a triode is basically, if I draw this whole region, so after this point it saturates, so this whole region is called triode region. So basically it is, you can say it is the combination of linear region, okay, plus until pinch off point. So we go all the way to the end of linear region, and then from this end of linear region to the pinch off point, this whole region is called triode region. So this equation is applicable to triode region. So if we plot ID versus VDS using this formula, okay, so it will nicely follow the curve, but at this point, this is our pinch off point. But at this point, beyond this point, so if I take, for example, this point, okay, at this point, this formula does not apply. Okay, it fails. So this formula fails here because this is the path. This is the path that is given by this formula. Okay, but actually this is not the characteristic of a transistor. The actual characteristic of a transistor is that it saturates. Okay, so beyond the pinch off point, the current saturates at this value. Okay, it is always the same after that. However, the actual formula is shown by this dotted line, but we know that the transistor saturates. So that's why the gradual channel approximation that we considered while driving this, that fails. Okay, so you have to remember the boundaries in which this formula is applicable. This formula is applicable only and only in let's say in this region. It is applicable in this region. It is not applicable beyond the pinch off point. Beyond the pinch off point, our current saturates at the maximum value. Okay, that is the whole. So again, it is shown in the slide. What I was saying, that when we have this condition, remember this was the condition for pinch off, and by this we mean that when this is equal to this, the whole current becomes zero, and we say that there is no charge in the channel. However, as we discussed, that this is the pinch off point, so the current is the charge is not exactly zero, but in reality it is very close to zero. Okay, we still have the current flowing, because if there is a current, the current should remain constant along the whole channel. Okay, you cannot have a discontinuous current. The current is continuous. That's why this point is confusing somehow, that the charge is zero but the current is not zero. Okay, and we had a discussion on this, why this is the case. From energy, we explained it from energy band diagrams. Okay, so again, this is about pinch off. So you see, it is this is the pinch off point. So beyond the pinch off point, you see that the curve is very steep, which means if there is electrons that come to this point, they will move very fast. So the electric field beyond this point is very strong, and even if you have a very little charge, the charge per unit time is the same as in the other channel. Okay, So this explains the pinch off point. And if we see to the graph in which there is the dimension x along the channel, and on the other side if we have the average velocity, so you see that if this is our pinch off point, you see at the pinch off point the velocity is huge. Okay, it is something like more than 10 raised to the power 8. Okay, while in the rest of channel the velocity is not that much large. So again, this is the same slide. At beyond pinch off point, current saturates at a maximum value, and the formula is not further followed. So this is the complete summary of characteristic of a square law device. So if we have number one, if we have VGS that is greater than VT, okay, what that means is that the transistor is on, okay, and VDS is less than VGS minus VT. This means that you are so if I draw this curve, okay, so that means this is the point where VGS is this VGS is equal VGS minus VT. So this is the pinch off point. So remember that at the pinch off point we have this condition. So what this means is this region. The first case represents this region. Okay, so that is the triode region. So in the triode region we have this formula. The second case is when the transistor is on and VDS is greater than VGS minus VT. This is the saturation region, and the current is you see it is constant. There is no variable term. There is no VDS. So in the saturation region it is independent of VDS. It is constant. Okay. So what about the linear region? So this was the first case. So basically the linear region is, I would say, 1.A. It is a special case of the first case. It is a part of the triode region, and it happens when VDS is very less than VGS minus VT. So if I draw the curve like this, and this is our saturation point, okay, this is our pinch off point, and at this point it is VGS minus VT. So what that means is that you are far beyond this point and you are in this region. Okay, so if you apply that approximation, that VGS is very less, so you see that there is a square term. So if VDS is very less, the square term will make it more less, and in comparison to this term you can neglect it. Okay, so that's why in the linear region you have this equation, and this is the same equation that we saw earlier when we were dealing linear region separately. So this is the same equation. So you see that the equation is very generic. The equation in the triode region that we derived in this lecture is very generic. From that you can reduce the saturation equation and also the equation for linear region. So let me stop here for this lecture. This wraps up our discussion on the square law model, and in the next lecture we will continue with the velocity saturated device and how we can develop equation for velocity saturated devices. Okay.